All right, so we wrap up this part talking about that decimal number we see on the periodic table. That decimal number is a weighted average, like I said, taking into consideration the different isotopic forms that that particular element can have out there in nature. It has to take into consideration how much it weighs and how its relative abundances. So you may not have run into this actually means summation. That means summation. Summation, of course, maybe means to add. And that is a Greek letter, capital sigma. And it means summation. So what it says, basically, is that for each isotopic form, you have to multiply how much an atom of that isotope weighs times something called its fractional abundance. And actually, I'm going to tell you here in a minute, fractional abundance is simply percent abundance, sorry, I'm butchering writing that, divided by 100. So it kind of looks like this then. We're going to add up terms until we run out of terms. We're going to take the first isotope, how much it weighs, times its fractional abundance, plus the second isotope, how much an atom of that particular type of isotope weighs in AMUs, times its fractional abundance. And we're going to continue the process until we run out of isotopes. And it will continue on and on and on. Oops. Let's see, it's not going on. Is it going on? There it goes. Okay, go back to this one. So that's what I said back here was you keep adding these, basically the product. You multiply these together and then you add them. Multiply these together, added to these multiplied, okay, and you add them up. We're going to do an example coming up, and your homework has an example too. So as I said in that formula, remember you're probably going to be given your abundances in percent abundances, and to get it back to fractional abundances, just divide by 100. So we're going to go ahead and look at copper, and we're going to come up with a weighted average atomic weight for copper, given these two isotopic forms of copper. So here we go. So you might want to refer to these numbers that we're going to use in the next few slides, coming up with the decimal number for copper. Now, one of the things, in case I forget to mention it, is you can look at copper on the periodic table and look at what the decimal number says, and that actually, decimal, oh my goodness, I can't spell, number, whatever that decimal number is, that's actually what we're trying to get here, okay? So, oh, and the other thing is I often like, if I am given I'm trying to work a problem coming up with the average atomic weight, I oftentimes put it in a table form like this so I don't screw up. And if you do a few of these, you kind of know what I mean. So we're going to apply this summation formula, and there's two isotopic forms, so we're going to have two terms added together. So actually we're going to have two terms that are multiplied, and then we're going to add those together, if that kind of makes sense. So this is for the first isotopic form of copper. This would be our copper 63. We said that it weighs 62.930 AMUs, and its percent abundance was 69.09. So its fractional abundance is 69.09 divided by 100, right? So then we're going to add that to information about the second isotope. The second isotope was copper 65. It weighs, a copper 65 atom weighs 64.928 AMUs, and then its percent abundance was 30.91. If we divide that by 100, we have fractional abundance. So, voila! Now if we do that, we should come up with a decimal number of round two significant figures, and I think I have a slide coming up later to tell you how to round these, but we're going to go with two decimals, and it's 63.55 AMUs. And again, you can check that against your periodic table for copper. That's the average atomic weight based upon these isotopes and their relative abundances. Very good. So just to kind of show you oh, this is, I see I put this slide in here to kind of show you how the units work. If we look at pick on copper 63, it weighs, for one copper atom, it weighs 62.930 AMUs. And then if we go with the the percent abundance is 69.09, so this is what it means. Okay. And if we add that to the other isotope, similarly, we end up with 63.55 AMUs in one copper atom. I thought I was on this slide. So this is to kind of look at if you what that looks like. If we look at the two isotopes, copper 63 and copper 65, if you split the difference, it looks like copper 64. It looks like if they were in the same abundance, it would be copper. It would be weigh 64 AMUs. But instead, what we came up with actually was a value of 63.55 is our weighted average, because the lighter isotope is more abundant than the heavier isotope. Now, taken to its extreme, I kind of talked about hydrogen having two isotopic forms, naturally occurring isotopic forms. The light one is much more abundant than the hydrogen 2. So if you were just to kind of do a simple average, you would come up with 1.5 AMUs was how much a hydrogen atom should weigh. But since hydrogen 1 is so much more abundant, when we come up with a weighted average, we actually come up with 1.008 AMUs is going to be the decimal number for hydrogen. So it's definitely weighted on this side because this is much more abundant than this. And if you apply the formula like of calculating average atomic weight, then it will always come out right. It will take that in consideration. So now you have these are due, and this is where I say you must show your work, because some of these, I don't know if all three of them, but are basically taking information about an element and coming up with an average atomic weight. And that answer, you can check your answer by looking at the periodic table, looking at the decimal number. So feel free to do that. On your Unit 2 exam, I can promise you'll be given isotopic information, and you'll have to go through the process of a weighted average to come up with an average atomic weight.